Hello everybody, Jai Hind, Vande Mataram. This is Kunal Mehta from Make Me Scientific, and in this video lecture we are going to take up the projectile motion, a special case, that is projections from a height. So basically this is a part of vectors, standard 11 physics. So here we have a building whose height is h, and then there is a ball which is being thrown upwards at some angle with respect to the horizontal, that is theta. Now that ball follows the trajectory, and the trajectory is parabolic in nature, and finally it hits the ground somewhere over here. Now, from the bottom part of the building to where the ball strikes the ground, that distance is our range, and we need to find out that. Then from time is equal to 0 to time is equal to, say, capital T, here time is capital T, the entire time of flight is capital T over here. So if you do not understand the projectile motion, the first part or the recent ones, the links are given in the description. You may please watch that video first and then this video. All right. Now we have three equations of motion. Now these three equations, motion has their own constraints. We can only use them for an object in a straight line, whereas this ball is actually following a curved path. So technically we can't apply these three equations for this ball. But we have a solution to that, right? What we are going to do is, this is a light, and say for example, I turn on the light like this. Now, say for example, this ball is here and its shadow on x-axis would be falling somewhere over here at time is equal to 0, right? I'm switching off the light to avoid too much of brightness over here. Now, suppose if this light is on, and during this journey, the shadow of this ball on x-axis would be here. When the ball reaches over here, its shadow would be over here. When the ball reaches over here, its shadow on x-axis would be here. And when the ball reaches here, on x-axis, the shadow reaches over here. Finally, the shadow and the ball, they both of them touch each other over here. So if you look carefully, during this entire motion of the ball, the shadow travels along one dimension in a straight line along x-axis. So you can apply these three equations for the shadow of the ball along x-axis. We can even do one more smart thing. If I turn on the light in this manner, then what do we have is the shadow of this ball will be casted along y-axis, because the light is going to come like this and it is going to obstruct the ball. Like the light coming from here, there is an obstruction, so the shadow will be casted over here. Now, if the ball is here, its shadow is here on y-axis, because this is our y-axis, this is x-axis. When the ball reaches over here, the shadow of this ball goes above the height of the building, and we don't care what is happening above the height of the building. But technically, its shadow will be away from the building. When this ball reaches over here, its shadow will be somewhere over here. When the ball reaches over here, its shadow is somewhere over here. When the ball touches the ground, its shadow falls over here. So if you look at a same particular ball which is traveling a curved path, there are two shadows, one coming down along the y-axis and finally reaching here, and the another ball shadow is traveling along positive x-axis. So you can apply these three equations of motion for this shadow as well as this shadow, and that's what we are going to do. Now, there is one more thing that you need to understand. Since we are dealing with lot many vectors over here, you please understand that all vectors along positive y-axis and positive x-axis will be considered as positive, and any vectors which are in the direction of negative x-axis and negative y-axis will be considered as negative. We have to apply the sign conventions. For example, acceleration due to gravity is always downwards, because the earth will always try to pull this ball in the downward direction, which means the direction of acceleration is the direction of force. So G is pointing downwards. So if you consider the ball to be at the origin, G is downwards. So G is considered as negative. Now, for this shadow of this ball along y-axis, initially the shadow was here, After some time, the shadow goes down. So the displacement of the shadow is from here to here, downward direction. So that will be considered as negative, right? When the ball reaches from here to here, the displacement of the shadow is positive because it is along positive x-axis. That will be considered as positive. Okay. Now, one more thing, when the ball is being thrown up at some angle with respect to the x-axis, there are two components of the velocity. One is ux, that is u cos theta, another is uy, that is u sin theta. As you can see that uy is pointing upwards, it is along positive y-axis, so it will be considered as positive as per our sign conventions, and this u cos theta is along plus x-axis, so this will also be considered as positive. So now let's do it. Let's apply the equation of motions in 1D for both the shadows. Now what I'm going to do is I'm going to use this equation. So this is our first part. I'm going to use S is equal to ut plus half a t square. I'm going to use this equation for the shadow along the y-axis. So I'm going to basically apply it for this shadow. Okay. So I'm going to write down Sy, that is equal to uyt plus half ayt. You can only substitute y under the vectors because time is the scalar quantity, so you can't, and rest all are the vector quantities. This is displacement, initial velocity, and the acceleration, right? So when I say Sy, the ball was here and finally the shadow of the ball was here. So the displacement is in the downward direction and the displacement is equal to height of the building. And as per our conventions, I'll have to take minus sign. That is equal to uy is u sin theta. Since the initial velocity is upwards, I'm going to take u sin theta as positive. Now plus half, acceleration along y-axis is always negative, times, sorry, this is square, times t square. Now, at present, I don't have any values to this, so I'm not worried about this particular part. But if you are given the values, then you need to substitute the value. In most of the questions, the height of the building will be given, initial velocity and the angle of projection will be given. Substitute, you will get the answer of the time. Right? Now, what we are going to do is, instead of small t, I'm going to use minus h, that is equal to plus u sin theta plus half minus g. I'm going to write down time of flight times t square. Why did I do that? Because when the ball was here at that time, time was 0, and when the ball reached here, the time was equal to time of flight. So meanwhile this ball reached from here to here, its shadow reached from here to here, so the time is basically equal to time of flight, right? I forgot one more t over here, so here time of flight is also going to come up. So it is ut, so capital T square. So our final equation is minus h, that is equal to u sin theta times t minus half g t square. Substitute the values and you will be able to find out the value of time. Now the second thing what I'm going to do is I'm going to find out the range. And for range, since this shadow travels along the positive x-axis, I'm going to use the same equation along plus x-axis. So I'm simply going to write down Sx, that is equal to uxt plus half axt square. Now the acceleration along x-axis is 0 because in projectile motion there is no acceleration along x-axis. That is due to the fact that there is only air resistance downwards. So there is only gravitational force downwards. So no component of force is in this direction. So no acceleration. So the velocity in this direction remains constant. So simply this part goes off. So Sx is basically when the shadow of the ball was here, when the shadow of the ball reached here. So when the ball went from here to here, the shadow traveled a distance equal to r. So simply Sx is r when I will substitute the value of t as capital T. So time is equal to 0 to time is equal to capital T. The displacement is basically equal to the range, positive range, and this is plus u cos theta, and everything is positive because u cos theta is in this direction. Now, So the final equation is range is equal to u cos theta times t. So this is your first equation. This is your second equation. All right. Now, the third thing is, suppose if I want to calculate the velocity at this particular point. So that's very easy. I do know that the velocity is always tangential. So this is our velocity. Now it will have two components, right? One component will be along y-axis, another component, this is along x-axis, another would be along y-axis. So I'm not worried about this part because ux is u cos theta. So here again I'm going to get u cos theta. That is due to the fact that since there is no acceleration along x, so at anywhere the x component of the velocity remains the same. Even over here, if this is your velocity, x component is still u cos theta, right? I'm only worried about the y component. So let's say here time is small t. Okay, so this is our third part, and at time t I'm going to use v is equal to u plus at. Since I'm interested in finding the velocity y component, so I'm going to write this as uy vy ayt. I'm supposed to find out vy here the velocity y component. So vy is equal to u sine theta. That is going to be positive because initial components, this is initial velocity is y component, that is this one which is positive, times t, but here this becomes minus g times t, right? So this is our equation of vy, and you know that this is vx, that is equal to u cos theta. So in terms of vectors, suppose if I want to write it down, the final velocity over here is suppose v. This final velocity is equal to x component, that is u cos theta times I cap, right? Because it is along positive x-axis. But this part is u sine theta. I'm sorry, I made an error. This t should not be here, right? So that is u sine theta minus gt times j cap. So this is what is going to happen, right? This is a in general formula, you can apply it anywhere, right? So these are our equations of motion for the projection from a height.